All right, greetings, YouTube. Beautiful mind here. We're continuing our. We're continuing our exploration of Chapter 3 on applications of differentiation, and today we're going to be looking at section 3.2, using second derivatives to find max and min values and sketch graphs. A couple of objectives here. We like to classify the relative extrema of a function using the second derivative test. And thank you. And we like to graph a continuous function in a manner that shows concavity, right? So let's start off with some definitions. Suppose that f is a function whose derivative f prime exists at every point on an open interval I, or in an open interval I. Then f is concave up on I if f prime is increasing over I, right? So, if we look at this example here on the bottom left, we have a curve. Concave up means that the derivative is increasing, right? Because if you look at the derivative here, first it's going from negative to positive, right? So it's increasing. The slope of the line on the left is negative, the slope of the line on the right is positive. So f prime is increasing. And then we say f is concave down on the interval I if f prime is decreasing. So with the one on the right, the slope of the tangent line is going from positive to negative. So that's what we consider to be concave down, right? So concave up, f prime is increasing. Concave down, f prime is decreasing. Another way you can look at it, it's like a cup, right? So if it's concave up, the cup opens upward, right? It's like the cup is opening up. Concave down, the cup opens downward, okay? So we have this theorem for a test for concavity. If f double prime is positive on an open interval I, then the graph of f is concave up. In other words, f prime is increasing, so f is turning up on I. If f double prime is negative on an interval I, then the graph of f is concave down. F prime is decreasing, so f is turning down on I. Okay, let's see. So we have another theorem that says the second derivative test for relative extrema. Suppose that f is differentiable for every x in the open interval on a to b, and there's a critical value c in a to b where f prime is equals 0. Then f of c is a relative minimum if the second derivative is positive. So the second derivative being positive means it's concave up, so that means that critical value should be a low point. And then f of c is a relative maximum if the second derivative is negative. If the second derivative is negative, that means the function is concave down. That means we should have a max, right? So for f double prime is equal to 0, the first derivative test can be used to determine whether f of c is a relative extrema. Okay. So that was kind of a mouthful. Let's work a few examples to see it in action. We're asked to graph the function f given by this and find the relative extrema. Okay. I'm going to try to do this without looking at the notes and get as many details as I can and be as concise as possible. So far, we have the first derivative and second derivative at our disposal. So it is a good idea to go ahead and find the first derivative and second derivative. Right? So then we should be able to do this quickly. F prime, so take the derivative, 3x squared, right? Plus 6x minus 9. And then the second derivative, f double prime, let's see, so the derivative of the first derivative, 3 times 2 is what? 6x plus 6, right? So then let's find our critical values. Let me get my space. Let's find our critical values. So first, let's look at the values that let's start with the first derivative equal to 0, right? So what values of x? So what we want to do is set f prime of x, set it equal to 0 and solve. So we're going to have 3x squared plus 6x minus 9. We want to set that equal to 0 and solve. Okay. Let's see. It looks like we can factor out a 3, or we can divide all terms by 3. If we do this, we'll get x squared plus 2x minus 3 equals 0. All right. And then let's see, we should be able to factor this into a form like this, where we have x and x. This tells us our signs are opposite. So one is positive and one is negative. This tells us that the larger is positive So I think it's 3 and 1. Let's try positive 3. Oops. Positive 3 and negative 1. 3 times negative 1 is negative 3. 3 plus negative 1 is a positive 2. Okay. So then from here, when we solve this, we get x equals negative 3 or 1, right? So what this tells us is that when x is negative 3, our derivative is going to be 0, all right? So that tells us that that's a candidate for either, now we could use the first derivative test to verify whether it's a local max or local min. Let's go ahead, let's plug these into the second derivative, right? So the second derivative, we have 6x plus 6, right? So then f double prime is 6x plus 6, right? So let's plug in, let's evaluate f double prime of negative 3. Okay, that's going to be 6 times negative 3 plus 6, 18, negative 18, so negative 12. But notice that this is negative, right? So with the second derivative being negative at this x value, that implies what, that is concave down. So then that should be a relative max at x equals negative 3. And we should still verify it with the first derivative test. Let's evaluate f double prime of 1. That's going to be 6 times 1 plus 6. So that's 12, which is positive, right? So the second derivative is positive at the second point. So that means our graph is concave up at that point. So then it should be a relative minimum at x equals 1, right? And then we can use the first derivative test to verify. Let's go ahead and look at the, let's use the first derivative test really quick. Okay. So we're considering when x is negative 3 and 1. Okay, so like for instance, so like if we consider f prime of x, these were zeros, right? So for instance, a number to the left of negative 3 is f prime. I'm going to use it right here. 3x squared plus 6x minus 9. Okay. So if we try a number to the left of negative 3. So if we plug in negative 4, let's plug it in right there. So if we plug in negative 4, that's negative, double negative is positive. So the first derivative is positive here. So the first derivative being positive means our function should be increasing on this interval. Number between negative 3 and 1 to test is when x is 0, we're going to get negative 9, we're going to get a negative result, right? So our function should be decreasing here. And then a number to the right of 1, let's plug in 2. So if we plug in 2, this is positive. Let me see, that's 12. It's 24 minus 9. So the final result is positive, which means our function should be increasing, right? So from the first derivative test, this tells us that our function is going to be increasing on this region and then decreasing and then increasing. Okay? So that confirms that we should have a relative max when x is negative 3 and a relative min. Okay, so we have our critical values, basically the peaks of the mountains and the bottom of the valleys. And then we also confirmed that it's concave down when x is negative 3, it's concave up. So then we take those critical values and maybe choose like a few additional points. Like you can just choose a few additional points and plot them. All right, so let's do that quickly. So like we'll make a table x and y. Let's go -5, 4, 3, 2, 1. 0, 1, 2, 3. Right. I just chose those x values. I'm just going to find the corresponding y. So I'm just doing a sketch, right? And if we plug these into the original, let's get a copy of the original. So we have this f of x equals x cubed plus 3x squared minus 9x minus 13. Okay, let's cut that. And we'll paste it here for reference. Let's move this down. Okay. So then, and let's choose a different color. So now the corresponding y's, and actually what I'm going to do, I'm going to use my calculator. I am going a little bit quickly. I'm trying to get class in like 50 minutes on the money. So I'm trying to do what I can in 50 minutes. Okay, so what I'm going to do in the upper left-hand corner, I'm going to go to my y equals. We got this x cubed plus 3x squared minus 9x minus 13. Okay. And then we just want to plug in those different values. So I'm going to call on that function that I just typed in. When x is, and actually we can just pull up the table. Let's go to table set. Table start, we want the table to start at like -6. Change by 1, okay, let's quit. I'm just gonna, I think all of these, you can pull it up on the table. Nope. So you see the -5, 8, -18, -4 is 7. -3 is 14. Oops. -2 is 9. -1, and again here, -1 we got -2. 0 we got -13. 1 we got -18. At 2 we got -11. And at 3 we got 14, right? So we just found the relative extrema and a few additional points. And earlier we said that when x is -3, that was a relative max. So let's label that. We got that this was a relative max, and this was a relative min. Okay. I really just want to do a quick sketch. Get a text box. Let's go space. Nope. Okay. Paper. Like this. All right. Okay. So let's see our x values. Our x values go from, we kind of went from -5 to 5, we went from -5 to 3, that's fine. Our y values went from like -20 to 20. Okay, so we can go like 5 to 5 on the x's and 20 to 20 on the y. So let's do this paper. Let's change it to this. So we'll let this be our origin. This will be our positive x direction. That's fine. This will be our positive y. Okay. Now let's see. We said 5. Let me see. 1, 2, 3, 4, 5. That's fine. 2, 4, 6, 8. Okay, let's do it like this. We're gonna go 2, 4. We can go by ones. 2, 4, 6, 8. Let's see, on the y-axis, we said 20 to 20, 2, 4, 6, 8, 10, 12, 14, 16, 5, 10, 15, 20, 4, 8, 12, 16, 20. Let's go by fours. 4, 8, 12, 16, 20. This will work. So on the y-axis, we went 4, 8, 12, 16, 20. Right? 4, 8, 12, 16, 20. And then on the x-axis, I think we went like this: 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8, 9. These are our negative values. These are our negative values. Okay. So then let's plot these points. So when x was -5, we got what? -18. That's here. All right. So that's -5, -18. -4, 7. That's about here. -3, 14. That's one here. -2, 9. It's about here. Okay. -1, -2. There's here. This one. 0, -13 is about here. Hmm. 1, -18. Okay. 2, -11 is about here. And 3, 14. They are having so much fun over here. Okay. So then if we connect this with the smooth curve, again, we got our max, we got our min. I'm just gonna do like this. There for these points, for that point, this point. It was a little off, but it's close enough. Okay. Let's go like this. Paper. Okay. So we got a rough sketch. It might be a little off. -4, 7. Oh, -4, +7. And I definitely put that at -7. So that's, I was like, why is that off? All right, -4, this needs to be here. Yeah, it's better. And then these guys. Okay. Oh, this needs to change. Okay. So we got a graph like this. Let's see the time. Let's see, how do we do? So it says first find the first and second derivatives. I think we got both of those results. So, solve f prime equal to 0. So they got -3 and 1. So -3 and 1 are critical values. Okay, so I think we got those results. Use the second derivative test with -3 and 1. When x was -3 into the second derivative, we got a relative max. I think we got both of those results. And then we found the corresponding y's for -3 and 1. Okay. So we got our relative max and our relative min. We got those. So they plotted those, and then they just plotted a few additional points, and they get an image like this. So now in this example, we're asked to graph the function given by this and find the relative extrema. Okay, so let's do the same thing or something similar to what we just did. We're going to find the relative extrema. Let's start by looking at the first. Let's go ahead and pull the first and second derivatives. Okay. So then we got this k of x equals e to the 2x minus e to the x. Then so the first derivative, so the derivative of e is itself times the derivative of the power, which is going to be 2. So it's going to be times 2. Minus e to the x, right? Because the derivative of e to the x is itself. Okay. And then let's go ahead and look at k double prime. So it's going to be 4 e to the 2x minus e to the x. Okay. So then the critical value, sorry about the back noise in the public space. We need to look at when the first derivative is 0. So we want to take this k prime that we found, copy and paste. And we want to set that equal to 0. So we want to set k prime, set it equal to 0. Let's see what we can do. Okay. So then we're going to say this 2 e to the 2x minus e to the x. We want to set that equal to 0. Okay. Let's see. It looks like we can factor out an e to the x, right? Let me think about this. So e to the 2x, all right? Because if we had e to the x squared, a power to another power, we multiply, so we can work reverse. If we're multiplying the powers, that's the same as e to the x squared. So that's e to the x times e to the x. So we should be able to factor out one of the e to the x's like this. Oops. E to the x, and we're going to be left with 2 e to the x minus 1. So then if we set each of these to 0, so I think with e to the x, that I don't think it'll ever be equal to 0, right? What value of x makes it 0? Because e to the x is entirely above the x-axis, right? So that one won't be 0. Let's try this other one. Let's say, or we got this 2 e to the x minus 1 equal to 0. Okay? So if we solve for 0 from there, we get e to the x equals 1/2. We get e to the x equals 1/2. How you doing? Okay. And then take the natural log on both sides. This. These cancel. This comes out of the exponent. So then, you can just leave it as the natural log of 1/2 for now. Just leave it exact. Okay. So that's the only critical value we got, whatever that number is, right? The other one, there was no solution, so we got what we here. So this is our candidate. So then we can take this and plug it into the second derivative and see what kind of result we get. So we got the natural log of 1/2. Okay, let's see if we can do it by hand. Let's copy. Paste. So now let's look at k double prime of the natural log of 1/2. Okay. That's going to be 4 e to the 2 times what? Okay. instead of plugging in there, I mean, we could do it by hand. I think it's gonna take a little bit longer than I want to do it, and we can. I might come back to. I'm trying to go quickly because I'm trying to get set up for class and stuff. So what I'm going to do is just plug it in over here because I think it's something simple, right? So if we say 4 e to the 2 times what natural log of a half closes off the exponent minus, and then e to the power of natural log of a half is just going to be a half. Okay, I think I got it. So let's do this. Let's do this. We want to evaluate k double prime of natural log of 1/2, right? That's what we want to evaluate. So this is going to be the same as a power to another power you multiply. So I'm going to rewrite this as 4 e to the x squared minus e to the x, right? So then this is going to be the same as 4 e to the natural log of a half squared minus e to the natural log of 1/2, right? This is why I paused before, because I was like, this is where I was trying to get to. And the whole point of doing it this way, this natural log and this e, the inverses, so they cancel each other. And this power comes out, right? Same thing here. So then we have 4 times 1/2 squared minus 1/2. And this is going to be what? A 4th, that's 1, this is positive 1/2. Again, this is positive. So because this critical value is positive in our second derivative, that means it should be concave up. That means we're considering that should be a relative minimum. Okay, trying to wrap up. Okay. So that should be a relative minimum. So we should have a relative minimum value at x equals, I think it was the natural log of a half. Whatever that number is, right? So we have our critical, let's go ahead and crunch that number. So then the natural log of 1/2. So it's approximately negative 0.7. Right. So this is approximately 69, 31, 47. 69. Oh, you did. Oh, I didn't charge my pen enough. A few seconds. Supposedly a 15-second charge. Well, when I first got it, 15-second charge was supposed to charge it, keep it charged for 30 minutes. So we'll see how well we do it. 60. We got 69. 69, 31, 47. 69. Okay. All right. So that's just a decimal approximation. So then we can just choose a few additional points, because this was the only critical value that we got. We said it's a relative min. And we should put it in the first derivative test, the test on the left and the right, just to make sure. And just for the sake of time, I don't think I'm going to find those few additional points. I'm just going to kind of go with it. I just want to shrink this down, get it on my page. Just for the interest of time. Okay. So again, we got that was a relative minimum there. And then to plot, we were just going to choose a few additional points. Plot the points with this relative extremum, right? So let's look at the prepared notes. First, find k prime and k double prime. I think we got both of those results. Solve k prime equal to 0, and they got natural log of a half. We got that same result. Second derivative test, they got a positive 1/2, which is the same thing we got, which is positive. So that means that our function is concave up for that critical value. So that means this is a relative minimum. And then if you take that natural log of a half and plug it into the original, that gives you the corresponding y. So now we have the coordinates of the relative minimum. Then you just choose a few additional points, plotting a few more points, we can make a set, right? We have our minimum with a few additional points to get a graph like this. Right? Well, I guess that's honestly the best explanation I've done of those in the past. Like in the past, I think I would actively looking for like x-intercepts and y-intercepts, which is nothing wrong with that, but sometimes they were getting like really nasty, right? So since this discussion was only about relative extrema, just find the relative extrema, find a few additional points between and beyond the relative extrema, and then plot it all together, right? I know that's like a gross oversimplification, but okay. So the quick checks, I usually leave those as exercises for you. We can talk about and go through any of them. And let's take a look at this theorem. So finding points of inflection, right? So the first derivative tells us whether the function is increasing or decreasing at any given moment, right? The second derivative tells us if the function is like concave up or concave down. So then what we mean by this point of inflection, that's where the graph is going to change from concave down to concave up or vice versa, right? So if a function f has a point of inflection, it must occur at a point x naught where the second derivative is zero, where the second derivative does not exist, right? So that's where it goes from concave up to concave down, and that happens when that point plugged into the second derivative is either zero or it does not exist. The quick check I leave as an exercise for you, that one as well. Okay, so then here we have an overview for a strategy for sketching graphs. So the first suggestion is find the derivatives in domain, find f prime and f double prime, and note the domain of the function. Identify your critical values, find the critical values by solving f prime equal to zero and finding where f prime does not exist. And then find the corresponding y for those critical values. You want to determine whether the function is increasing and or decreasing and identify your relative extrema. And basically you want to find those critical values and plug them into the second derivative to see if the graph is concave up or concave down. And then you want to find your points of inflections using the second derivative. The point of inflection is what is going to occur where the second derivative is zero or undefined. So once you find the critical value, then you just want to make sure that it's like for it to be a point of inflection, the graph has to go from concave up to concave down or vice versa. Concavity, use the candidates for inflection points for step D to define intervals. Use the relative extrema from step B to determine whether the graph is concave up or it's concave down, and then sketch the graph, right? So that's a mouthful. It's a little intense. Let's give it a go. I got about a little over 10 minutes, right? Find the relative extrema of the function given by this, and then sketch the graph. Okay, let's give ourselves some space and let's give it a go. I think we can do it. Okay. Let me start by getting a copy of the original. We got f of x equals x cubed minus 3x plus 2. Okay, I'm going to take this and put it right here. Okay, so then the suggestion is first find your first and second derivatives. So f prime of x is going to be 3x squared minus 3, and f double prime of x is going to be 6x. Make sure I get that right. Okay. All right. So then the critical values, first we want to set f prime, I'll just kind of break the line. So then let's do like this. Let's do it. Okay. Oh, let's put on my headphones. They're losing life. Just trying to confirm.
disconnected. Looking for the Bluetooth signal. Because it says connected. Yeah, it's like something's not showing up.
Just fine. Okay. All right. So we want to find our critical values when the first derivative is 0. That's going to be our relative max and relative min. So that means we're going to, again, we want to set f prime of x equal to 0. So we have this 3x squared minus 3. We want to set that equal to 0 and solve. We can factor out the 3. So divide all terms by 3. We'll get x squared minus 1 equals 0. This factors into something like this: x minus 1, x plus 1. This times this is a minus. They're gonna cancel. Yeah, this is good. So then we get x equals -1 and 1. These are our candidates. So then we can take these and plug them into the second derivative, right? And this will tell us the concavity. Right? So then if we look at f double prime of -1, that's going to give us -6, which is negative. So that means it's concave down. Right? And then f double prime of 1 is going to give us +6. Again, that's positive. So that means our graph is going to be concave up. So what that means is that, let me see, we should have a relative max at x equals -1, and we need to find the corresponding y, and then we have a relative minimum value at x equals 1. All right. So then we just need to find the corresponding y from the original. So when x is -1, this is -1 plus 3 is 2 plus 2 is 4. Right. So this is going to be the point -1 comma 4. And then when x is 1, that's going to be 1 minus 3 is -2 plus 2 is going to be 0. So then 1 comma 0, right? And then let's find the point of inflection. So let me add the page. Let me see the time. I can hang out for another 10 minutes. Okay. So then let's find the points of inflection, points of inflection. Okay. So that's where the second derivative is going to be 0 or undefined. What's just 6x? So then if we have 6x equals 0, the point of inflection occurs when x is 0, right? And then, we should just make sure that when you choose an x to the left of this, I think we said it's what, concave down, and then x is on the right should be concave up. So we're just gonna go with this. Let's see if we can quickly put all this together. Point of inflection, and so if we plug this into the original, we get 2, right? So the point of inflection should occur at the point 0, 2. And just for the sake of time, I'm not gonna graph these by hand. I'm gonna just kind of piggyback, just because I'm kind of short on time. Okay, so we found the first derivative and the second derivative, plus or minus 1, and then we found the corresponding y's. Do we get that 4? Okay. So we should use the first derivative test. They use the second derivative test to tell about relative extrema. Keep going. So then points of reflection, the critical value was when, you said the second derivative is 0, we got x equals 0. So then the order pair was 0, 2. And then you see it all here put together. You see the relative max, the relative min, the point of inflection, where it's concave down, concave up, increasing, decreasing. All right. Okay. We're almost there. Trying to get you there. The quick check 4, I leave as an exercise for you. And let me see, graph this function given by this. And I think I'm just going to piggyback just because I'm kind of short on time. I'm going to piggyback on the notes that I've already prepared. So same thing here, right? If we're doing our derivatives, for instance, if for the first derivative, you got to use the chain rule that 1/3 comes down, you subtract 1 from the exponent, and then you got to say times the derivative, the inside function. And then when you go to do the second derivative, it looks like you're going to have to use the product rule. So it can get a little bit, kind of busy, right? So we get these results. Let me see. Second derivative. So we basically take the derivative of that guy. Well, we're not going to use the chain rule. I mean, the product rule, but it takes a little bit of effort to get to this, and you get that result. Okay, let's keep going. So then the critical value occurs when the first derivative is 0. So they set it as 0. You can divide both sides by 3. So if you have it to the power of 2/3, you can raise both sides to the power of 3/2, but 0 to the power of 3/2 is still going to be 0. So then you get 5/2 for x there. And then they found the corresponding y. So then with that critical value, you take that and plug it into the second derivative, and that tells you the concavity, right? So they got it undefined. Since the second derivative does not exist, the second derivative test fails, right? We can't use it. So instead, we're going to use the first derivative test. We tried to verify with the second derivative, but we got a an error or whatever. So then we use the first derivative. So basically, we take this x value when x is 5/2, and then we just need to test a number to the left and a number to the right in the first derivative. And then the first derivative tells us whether the function is increasing or decreasing, right? So then if 5/2 is 2.5, they chose a number to the left, they chose was 2, a number to the right, they chose was 3. So notice that they're both positive, right? When you choose a number on the left and the right, they're both positive. Since f prime is positive on both sides, 5/2 is not an extrema, right? It was a candidate, it was a critical value, but then it turned out to not be an extrema. And so if you choose a few additional points. So the point of inflection is where the second derivative is 0 or undefined. Okay. Let's go back really quickly. Since f double prime is never 0, right? We only need to find where f double prime does not exist. And since f double prime cannot exist everywhere, where f prime does not exist, we know that from step B that a possible inflection point is 5/1, right? So then they take that, they choose a number on either side to get the concavity. On the left of 5/2, the second derivative is positive. On the right of 5/2, the second derivative is negative. So it goes from concave up to concave down. So that means that's our point of inflection. So then you just choose a few additional points and combine them with this point that we found. So we have this point of inflection and you get something like this. All right. Okay. It was a little bit rushed, because I do have to start class in like 5 minutes. So just as a quick recap, section summary. The second derivative determines the concavity of the graph. So does the curve open upward or does it open down? If the second derivative is positive, it's concave up. The curve is opening up. If the second derivative is negative, it's concave down. If C is a critical value and F double primacy is positive, then F of C is a relative min, right? So if C is a critical value and the second derivative tells us that the curve is concave up, that means that C is going to be a relative min. If C is a critical value and the second derivative is positive, that means C is sitting on top of a mountain. So that means we're going to have a relative max. If C is a critical value and the second derivative is 0, then we have to use the first derivative test to clarify. Because sometimes when you try to use a second derivative test to verify whether something's a relative extrema, it fails, right? So then when that happens, you use the first derivative test to verify whether it's a max or a min, or to verify whether it's an extrema. If the second derivative is 0 or does not exist, and there is a change in concavity to the left and right, then the point x naught, f of x naught is called the point of inflection, right? So, yeah. And then finding the extreme in the intervals over which a function is increasing or decreasing, intervals of upward or downward concavity, and points of inflection is all part of a strategy for accurate curve sketching. Right, so we know how to find the peaks of mountains, the bottom of valleys, the points of inflection, where the graph is increasing, where the graph is decreasing, where the graph is concave up, and where the graph is concave down. All of these things I just rattled off are what the first derivative and the second derivative tell us about these curves, these graphs. Okay. And just in the nick of time, on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. Peace.